Greetings. Thank you, David, and good day to everybody. I'll go ahead and get started here. The subject David had asked for input on was this thing called atmospheric rivers. I imagine most have heard a bit about that by now, but I'll give you a bit of an update on that, and some people like to use the term rivers in the sky, and I'll explain that in just a moment. This photo in the background, by the way, is from January 2017 up near Sacramento, just to the north. You can see the flood inundation there, which was in fact an atmospheric river event meteorologically that helped trigger that. All right, brief outline. I'll define what an atmospheric river is, briefly answer the question, can we predict them? Talk about an application of forecasts of ARs called FIRO, a little bit on the epic water year 2017 and Oroville, and then the last item there, I'll move on to atmospheric river reconnaissance instead of that. All right, what is an atmospheric river? Well, this is a nice schematic from a Scientific American article by Dettinger and Ingram in 2013 that shows the west coast of the U.S., highlights California there. And you can see sort of metaphorically or schematically a ribbon of strong water vapor flux going on in the atmosphere offshore and hitting the mountains there, and then turning into precipitation over the mountains. I'll show you more about what that looks like in reality here in the form of a loop of a parameter we use to look at ARs oftentimes called integrated water vapor. It's the amount of water vapor in the atmosphere above the point if you took all the vapor and condensed it down to liquid. And the units are in centimeters. And right now you see one forming up and about to hit the coast. There it's hitting California, and another one hits, and then another one hits. Those three back-to-back over the course of a few days produced up to 25 inches of rain, and about up to a third or more of the annual precipitation for that otherwise dry period. All right. The topic's been percolating for about 15 years now, and not until very recently did our scientific field settle on a formal definition, which is described here. Let me just read it for completeness. It's a long, narrow, and transient corridor of strong horizontal water vapor transport that is typically associated with a low-level jet ahead of the cold front of an extratropical cyclone. The water vapor in an AR is supplied by tropical and or extratropical moisture sources. In other words, some of the water vapor can come from the tropics, but it doesn't have to. Atmospheric rivers frequently lead to heavy precipitation where they are forced upward, like by mountains or by something called the warm conveyor belt. Horizontal water vapor transport in the mid-latitudes occurs primarily in atmospheric rivers and is focused in the lower troposphere. The schematic in the upper right is another view of that example. The lower left is a schematic from a paper I did a couple of years ago using many different field experiments data, and it shows the mean characteristics in plan view of an AR. Basically, you got north or higher latitude to the, on the upper part towards the top of the diagram. The equator would be towards the bottom. The colored bill is the integrated vapor transport. The solid lines is the integrated water vapor, like we saw in that loop a moment ago. And what you see is that red area is the core of the AR. The gray represents the extent of the AR. And on average, they're about 800 kilometers wide, about 3 kilometers deep, and transport about 5 times 10 to the 8 kilograms per second of water vapor. I'll relate that in a moment to more meaningful terms. On the right is a vertical cross-section slicing across an AR. On the vertical axis goes up to like 12 kilometers, about the height you fly in commercial jets. Horizontal axis is about 1,500, 2,000 kilometers total. The blue contours represent the winds, and you can see the upper level jet there at about 60 meters per second and pushing 130, 140 miles per hour. In the lower part, you see the pink area. That's the AR. It's tucked in just ahead of the cold front, which is that gray area, and it tends to be associated with a low-level jet of about 25 meters per second or 50 knots. The bottom line is the upper air is really dry. Even though the winds are very strong, it's really dry. Down low, the winds are strong, not as strong as way up above, but it's much more moist, 10 times more moisture down low. Combine the moisture with the strong winds and you get large horizontal water vapor transport. One of the key events we've had recently, the one that hit Oroville, was in fact an atmospheric river. On the left, you see the integrated water vapor image of that, and on the right, the integrated vapor transport image. And As I'll come to at the end, we're developing a scale for ARs, and this would be what we call an AR Cat 4 on this new scale, and it would be of extreme intensity. I'll give you more information on those scales at the end. All right, how strong is an AR? How did we figure that out? Well, we used aircraft, research aircraft, including the NOAA P-3 and G-4, which do a lot of hurricane work, like in Florence recently, the NASA Global Hawk and Air Force C-130s, also are used for hurricane recon. This is a paper published last year. Bottom left shows the tracks of 21 different storms we sampled with ARs, and that track is where we took data from the AR and calculated the water vapor transport. Behind that, in the color field, is the frequency of occurrence of ARs based on satellite data, and you can see there's sort of a AR alley, heading northeast from Hawaii. And you can see the core, the most common area to hit shore is up in the Northern California, Oregon area. And there's the averages I showed a moment ago. There's that cross-section again, and that data. What I really want to highlight is if you look at that, 500 million kilograms per second of water vapor transport in a typical AR, that's about 25 times the average discharge of the Mississippi River. The Mississippi is, of course, liquid, whereas an AR is vapor. On average, there are only 3 or 4 of these at any given time in the northern hemisphere, and similarly in the southern. And they're doing something like 90% of the horizontal water vapor transport in the atmosphere. So these things really are, in many ways, rivers in the sky, but they're water vapor instead of liquid. Now I want to put this in perspective nationally, and I'll start by pointing out that if you look at historically year-to-year variability of precipitation using rain gauge data going back several decades, and look at how that varies from year to year relative to the mean precipitation that year, what we see is back east, very little variation from year to year, plus or minus 10 or 20% at most, about plus or minus 15. I'm from Michigan originally and lived in Florida and spent a lot of time back east, so you get a wet season or dry season. Each season has the potential to be rain or include rain. The yellow dots in the middle part of the country are more like plus or minus 25%. Then you get out to the southwest, in particular California, and we've got plus or minus up to 50% of average annual rainfall is the normal variability from year to year. Mother Nature has provided California with the most variable hydroclimate in the country, and it's largely a result of ARs, and let me explain that. The next slide highlights an analysis of the Sacramento or Delta catchment, including Sacramento and San Joaquin, and it looks at precipitation over the last century. This is a nice paper by Dettinger and Kahn a couple of years ago, and the annual precipitation is shown. Let me step you through. The black curve is the 5-year running mean of the total precipitation. You see some big ups and downs. And the interesting thing they did in this study was ask the question, if we took just the 5% wettest days each year, out of all the wet days, just take the 5% wettest ones, which is really just a handful, and ask how much did they contribute to the annual precipitation, and then add up all the remaining 95% of the wet days. The green curve is the remaining 95%. The red curve is the top 5% wettest days and how those vary from year to year. Visually, you can easily see how the red curve explains more of the variation in the total precip, meaning that essentially the 5% wettest days each year, how they vary, explains, from year to year, explains 85% of the variance in annual precipitation. Essentially, if we don't, and those 5% wettest days are almost entirely ARs. In short, if we don't get enough ARs in a given year, we end up drier than normal. If we get too many, wetter than normal. Of course, we have to factor in the strength a little bit, but a lot of it has to do with count. Are these things important elsewhere than just California? A couple of very nice papers recently, Glahn and Walliser, 2015, and Walliser and Glahn, 2017, show with these red dots the locations around the planet on the left where landfalling ARs are a frequent occurrence. And you can see Western Europe, for example, Western South America, even Western Australia, other parts of the globe are listed. Even in the polar regions, there's some impact. And on the right, you see the fact that even surface winds are often, high surface winds are often correlated with ARs as well at landfall, which has important implications for other facets of hazard preparedness and the like in the weather business. So we're learning a lot about ARs in California. We're sort of kicking the tires on the topic and inventing new tools. And as is not uncommon, we're leading the way globally on a problem that's relevant elsewhere. All right, how are we doing some of that work? Well, one of the things we've done is create a new center, which I'm the director of and have created, called the Center for Western Weather and Water Extremes. And in the upper left, you see a diagram there highlighting in yellow where atmospheric rivers are the cause of the most extreme daily precipitation. The blue is where the monsoon is. The green is where front range upslope storms like the terrible floods in the front range of Colorado in 2013. And the red is more traditional deep convection we see a lot in the Great Plains. I'll also highlight the red star there down in San Diego. That is our San Diego, mothership, so to speak, at Scripps Oceanography. We also have an office up in Sonoma at Sonoma County Water Agency, and the white stars are organizations where I've established collaborations and partnerships, including through projects I've gotten funded and programs I send funding to them to work with us so we don't duplicate capabilities elsewhere, and we develop a network of collaboration and partnership to solve these problems. Okay, so I was just introducing our center, and we have we're really trying to bring modern and state-of-the-art science and technology and hydrometeorology and related fields to really apply to the extreme events in the West. And we've developed a nice team there with students and postdocs and staff. We're doing a high-res model, and I'll show you more about that in just a moment, among other things. We're also producing some diagnostic outputs, and we post it on our website when we do so. And this is a product generated to support California Department of Water Resources, and in fact was done at the request of DWR meteorologists and climatologists to develop, with Janine Jones, Mike Anderson, and others have asked for this, and we've developed a mapping that shows each AR that hits the West Coast in a given year. On the left, we see water year 2017. On the right, water year 2018. And you can see the angles of orientation there are represented, as well as the intensity based on the color fill there. And I'll come back to that again later. Here's an example of the comparison between water year 2017 and 18. On the left are the weak, moderate, strong, and extreme ARs from 2017. And you can see how in 2018 there were quite a lot fewer, like about half as many. And on the right, you can see the major difference between the two water years. Also note the very stepwise nature of the accumulation for the year. Each one of those steps most often is associated with an AR. And if you look total, about half of 40 to 50% of Northern California precipitation comes in on the order of about a dozen or 15 ARs each year, each one lasting on average about a day. Can we predict ARs? Well, yes, but to a degree. Here's a tool we display on our website for the center, and we put out little outlooks online, and we do this in coordination with and sharing National Weather Service products, and we're using global models that others put out, but also some of our own data. What we see here on the left is a map. The color is essentially the AR in water vapor, and on the right, the color is the integrated vapor transport. This is how much water vapor is being transported in the red area you can see hitting shore. This, I believe, was the first one of these outlooks we ever did. It was back in 2016, and we were able to look ahead into the future. But how good are these forecasts of ARs? Well, this is an analysis from a paper a couple of years ago that showed a comparison of the forecast landfall position of an AR versus observed, where we use the satellite water vapor measurement to observe it. And the punchline here is on the vertical axis is the landfall position error in kilometers, and the horizontal axis is the lead time. And I'm just highlighting here that about 5 days lead time, there's about 500 kilometers error in landfall. This is saying basically that we may see an AR coming a few days ahead that could hit California, but we don't really dial into exactly where until we get closer in time. Let me highlight how we represent now, diagnose using model forecasts, the uncertainty in AR forecast position or strength at a given position. On the lower right, you see a red little square that's showing a location on the coast, and then that points to the upper left diagram, which is all of the different forecasts of AR integrated vapor transport, which I'll call IVT, from 21 different forecasts run by the National Weather Service. Each forecast is initialized with a slightly different initial condition, and therefore, due to the butterfly effect or uncertainty in weather forecast ability in the first 4 days, pretty good likelihood there's going to be another one within a couple days after that, and then we really don't know beyond 10 days. Now, on another slide, and just speak up if the slide's not advancing, we have an example from January 2017. Each one of these slices now, starting on the right-hand side, is the 0 to 1 day lead time. Then it's 1 to 2 days if you go to the left, then 2 to 3, 3 to 4. And what we see is if we look farther out in lead time for the same event when it made landfall, what we see is, say, at 5 or 6 days lead time, or let's call it 6 to 7, that you see yellow up there at about 44 north, and pretty low probability, 50%, and it's going to hit Oregon. But what it ended up happening was the forecast tended to bring the AR further and further south as the storm got closer, and we became much more confident in it about a day or two ahead that it would actually hit much of California. This is what we call DPROG-DT. It's a very interesting way to portray how forecasts change with time as an event is approaching. All right, let me do that again for the big storm that hit Oroville. And you can see here on the left the integrated vapor transport. The red is strong. And in the middle there, you see a moderate predicted AR there at 2 days lead time. In this case, the diagram, the forecast goes from left to right and goes out 7 days. And when we look at the damage that storm provided, you can see that on the left. Now we look at the forecast issued a day later, and we see a strong AR at 1 day lead time. And then at the day of, we see, in fact, that the AR had become even stronger and reached what we call extreme. And you can see here the red line, or the black line, highlights how that forecast at 2 days lead time was for a moderate strength AR, but when it hit, it was extreme. And that is an example, like for a hurricane, an analog would be if a forecast was 2 days before a Cat 4 storm hit the coast, it was only predicted to be a Cat 2 hurricane. That's sort of the magnitude here. Of course, we're not talking hurricane. This is an AR. It's a different animal, meteorologically, different impacts and all that. But that's sort of the magnitude of uncertainty that was present in that forecast. So think of it. 2 days before the big Oroville storm, the forecast was for a moderate AR, but what hit was extreme. All right, what are we doing to address that problem? We're developing there's a number of things. One of them I'll highlight here is we're developing a version of a weather model that focuses on ARs. This is what's happening in the weather business, is we have global models now run by the national centers, and then for different phenomena and regions and applications, we can embed a regional weather model and run it at high resolution, tailoring it to the problem at hand. So we at CW3E are developing that in support of DWR and the Army Corps of Engineers and others to optimize the performance for ARs. And here we see an example of a storm a couple of years back. The little dotted circles there are the dropsondes from aircraft, and we use those in many cases. We had those about a couple dozen to compare our forecast with the forecasts from the national centers. And we can do that partly by looking at ARs as an object. On the left-hand side, we have this new tool now to do this automatically. On the left-hand side is the predicted AR, outlined in black, and the color fill is vapor transport. On the right-hand side is the observed or analyzed AR when it actually hit a couple days later. And you can see some important differences. Now on the next slide, I'm looking at the performance of what we call the West Wharf model. That's our AR model on AR landfall position error forecast skill. And what you see in the horizontal axis is different lead times from 1 day out to a week, and the error in landfall position in kilometers on the vertical axis. And I'll highlight that the blue curves are our West Wharf model. And you can see in the first couple days they're doing as well as any other model we're tracking here, which are the major, some of the major models in the U.S. and the Canadian model. But as we get out to farther lead time, it's doing noticeably better. And then if we look at the intensity of the AR in terms of the forecast, we see something similar. Pretty similar uncertainty in the first 2 to 3 days, and then our West Wharf model does better as we get out in time. I should highlight that we are just building this right now. We really have just scratched the surface, in my opinion, on optimizing the model for our problem, and these early results give me substantial hope that we're on a good path for having a well-tuned model for AR prediction for the West Coast. All right, now we're looking beyond week 1, which is largely what that other thing was about, the last slide. Now we're looking out at week 2 and week 3, and this is supported under funding through the California Department of Water Resources AR program and the U.S. Bureau of Reclamation. And we're looking at, and now time goes from right to left, the lead time. And let's take the left-hand diagram, go from the right side of it, which is 0 hours or 0 days lead time, and you see the purple there, that's an AR, 1 day out from hitting the coast of Northern California and Oregon. Then it looks like the rest of that week, if you go to the left, the black vertical line, the rest of that week is pretty quiet. Now this part of the diagram, these 7 days are at 3 hourly time resolution. Now for the next week out is that blue area to the left is the daily sampling only. We're asking the question, does the forecast show an AR predicted? It didn't, in that second week, but we're not worrying about whether it's within, plus or minus 3 hours or 6 hours. We're just worrying about it day by day. And we see no ARs predicted that next week. And the very left-hand panel or column is what we call week 3. Now we're not even worrying about which day it hits, if it does, or if there's one in the forecast, but if it's even going to be active that week. And how do we know it's going to be active or not? We compare to climatology. If you jump your eye now to the right-hand diagram, the left-hand side of that has the arrow pointing to week 3, we see the reddish-orange colors there, which are greater than 0. That means there's a bit enhanced probability compared to climatology for AR activity in the Oregon, Washington coastal area during week 3. I want to highlight that we're developing these tools in collaboration. I got to skip ahead a little bit here. With a number of folks, including at NASA JPL. We're working very closely with Mike DeFlorio and Dwayne Walliser and others, and also with a couple of other organizations. And this is highlighting probabilities at week 3. In the bottom panel on the left, you see the sort of whitish to light gray color in California primarily. That means it's at 3 weeks lead time. We're seeing evident, suggestion of normal AR activity, nothing too active or inactive. Alrighty, I'm going to change gears here now to look at FIRO, or Forecast Informed Reservoir Operations. David, could you give me a time check?
You're doing fine. Keep going. If we have to go a little bit, it is 12:37. We target 1 o'clock, but if we have to go a little bit past it, this is great information. I'm sure everyone wants to make sure that they make the most of it. And the presentation just went black again.
Okay, I will go back to Skype.
There we go.
Is it back?
Was.
Share program. PowerPoint. Share. Okay, I'm relaunching. Let me know when it's back. And I'll introduce the concept in the meantime. So this is, it's back? Okay. I'm going to turn now to an application of AR forecasting that is emerging, and it's in the context of recognizing that reservoir operations, if we had good enough AR forecasts, might be able to take advantage of it. Historically, many reservoirs are limited, reservoir operations are limited in their ability to use forecasts, and we recognize that. And in response, we formed an ad hoc steering committee to look at a reservoir called Lake Mendocino up on the Russian River. It got hammered by the drought. There'd been a big AR right before the drought, and I'll show that in just a moment. Water was released, which is the right thing to do in that mode, because who knows if another one was coming. There could be a big flood. So they got the water out of the flood control space within a few days. But unbeknownst to anybody, the drought began. And that led to a pretty serious situation for that reservoir. And about a year after that happened is when a few of us got together, and Jay Jaspers and myself, proposed that we form this ad hoc steering committee to just at least look at whether or not there's enough skill in the AR forecast, because we knew ARs are the cause of the floods on the Russian and 50% of the precip. If the forecast skill of ARs was good enough to take advantage of potentially, and that led to the formation of our group. Here we see a photo at the top of the reservoir in that bad situation of drought, and ironically, not long before, the river had experienced high flows, not really a flood stage quite, but pretty close, all within the same year. It's actually not uncommon for this watershed to have both drought and flood experienced within the same year. Flood control operations are by the Army Corps, water supply operations are by Sonoma County Water Agency, and fisheries restoration, their endangered salmon, is led by NOAA. All right, now I'm going to show you a little bit about the reservoir and the watershed. On the left, what you see is the terrain map of the watershed. It's about 100 kilometers north-south, and you see the terrain goes up to on the order of about a kilometer or so. It's not very high relative to the Sierras, but it's substantial for a coast range. And it provides about 1.6 million acre-feet annual discharge. And it typically takes about 1 to 3 days for water released from Lake Mendocino to flow south past the town of Guerneville, highlighted in the bottom. Lake Mendocino itself can hold up to about 110,000 acre-feet in the summer, 68,000 acre-feet in the winter. On the right is a 2.5-year time period showing the reservoir conditions. On the vertical axis is the storage in acre-feet on the left. On the right-hand axis is the vertical axis is the cumulative rainfall. The green curve is the cumulative rainfall over the 2.5 years. And you can see the big ups and then the flats for the summer and all that. The big ups are ARs. The blue line is the actual water level behind the reservoir, so that's on the left-hand scale. You read that. The gold dashed line is the storage curve, and in the winter, of course, it's kept partly empty for flood control, and in the spring, it's allowed to refill. Notice how on the left-hand side, that blue curve climbs up right along with the gold line. That spring happened to be wet right when the reservoir could take advantage of it. Then the water was, used through the summer, and by the time we get to the middle of the diagram, we're in December of 2012. We get 2 big ARs that encroached into the flood pool. The reservoir did its job for flood control, and then the water was released. But then you see the green curve doesn't rise up very much more for the next year. That was the beginning of our multi-year drought, and you can see the blue curve then dropping off severely going into the next winter, and this created a lot of different important actions in water supply and fisheries, endangered species restoration and all that that were quite serious. The question is, can we save some of that water potentially if we had good enough forecasts that had to be released originally? If we could forecast ARs well enough, maybe we could keep it there day by day until a forecast says there's an AR coming, then it's released. And then if no AR comes like happened here, we end up with that water available for the summer. We formed a steering committee. I mentioned I want to highlight Mike Anderson, the membership. Mike Anderson from DWR, Levi Brecky from the Bureau of Reclamation, Mike Dillabaugh at the time this slide was made from the Corps. He's in charge of the operations, or was for the Corps there of that reservoir. Mike Dettinger of USGS, Rob Hartman from the National Weather Service at the time, Christy Jones at the Corps of Engineers at the time there in Sacramento, Pat Rutten from the NOAA Restoration Center, that's the fisheries side, Terry Talbot from the Army Corps of Engineers Research, Robin Webb from NOAA's research side. And we have support staff, David Ford, Arlene O'Donnell, and Ann DeBay. I want to highlight that because we formed it's important we had this team of people who were responsible. Some of the members were actually the ones responsible for reservoir operations. Others are engineers who are familiar with the topic in the area, and others are scientists like myself. All right, let's turn now to an example of what we're talking about hypothetically for this reservoir. And this is a scenario that our steering committee came up with. Do you see a blue line on the chart now?
Yes.
Okay, that's the 10-year average. This is the annual water year here on the horizontal axis, and the Lake Mendocino water supply storage on the vertical axis. And what we see is the flood control pool on the left, and then can fill it in the spring thing. But on average, you see it doesn't fill up by quite a lot. And here's what happened in 2013, the red curve, and that storm, the big AR. This is a nice image of that storm in December 2012 that encroached into the flood pool. And now back to the storage curve. Those two pulses were due to ARs. And the idea the committee came up with was, imagine 10,000 acre feet could be kept temporarily pending a forecast of an AR. So in other words, at the time that water was being released or starting to be released from the reservoir to get back to the flood control space, to recover the flood control space, that if there was no AR in the forecast out several days, then maybe hedge bets and keep 10,000 acre feet for the next day, and then look at the forecast again and go forward in time like that. And the number 10,000 acre feet came out of the steering committee. It wasn't pulled out of a hat. It was based on the knowledge of the people who operate the system. And that became our target. And what we call that is potential FERO-enabled additional water supply reliability, enough for about 20,000 homes for a year. Let me say, I haven't gone into where we've come from here, but I'll let you know that our preliminary viability assessment, this is a 5-year program. We've got a work plan developed by that steering committee. We're executing that. We're about 60% of the way through, and our preliminary assessment is that this is achievable with current forecast skill. In fact, more like 20,000 acre feet could be achieved without adding flood risk. But now we had the big 2017 year, and we're looking at the flood side more carefully, and we're also exploring what benefits could accrue if better forecasts were available. So we're pushing forward on the better AR forecasts and the more thorough consideration of the flood side. But early results are very promising. Now the next slide is about the fact that we have started another FERO effort on Prado Dam with Orange County Water District and the Army Corps of Engineers. It's a nice photo from Southwest Airlines flight looking northeast over the basin. You can see Prado schematically in the middle there, and the fact it's ringed by mountains. Very different arrangement than the Russian River. Here we see the mountains go up to 11,000 feet in some cases, and here's the watershed there you can see on the left. And on the right, these 3 panels show in 2017 3 different AR storms that all hit that area roughly, and how different they look from one another. I won't go into the meteorology, but they're very different meteorologically in terms of a larger scale, but in each case there was an AR that hit the area generally. All right, let me highlight some future directions here. Key is atmospheric river reconnaissance, and we did a demo in 2016 with Air Force C-130 help. They usually fly hurricanes, but with the big El Nino, I got a request in at the last minute that was supported for us to deploy 2 C-130s for 3 storms that winter in 2016. We worked out how to do that, more or less, and now we went back last winter and did it in 2018 with 6 storms, and this year we're proposing to do 6 more storms in 2019, maybe even 9 storms. And if we get another bite at the apple the following year, our goal is to get about 30 storms, and that'll give us enough data where we can evaluate effectively and reliably, will this method help us improve the forecast of AR landfall? Remember, for example, the Oroville incident was off by 2 categories in our new scale, and then also there's another example I'll highlight in a moment from this last winter. The AR intensity scale and AR categories. Let me highlight this other case I just mentioned a moment ago. This is from this March. This is a precipitation forecast from the River Forecast Center in Sacramento there, National Weather Service. Very good forecasts in general. Best in the country, by the way, but they still have errors. And what we see here is, the pinkish area at the bottom there is predicted to be up to 5 inches or so or more of precipitation 2 days ahead. And right on Santa Barbara and areas that were hit by the fire and by the terrible Montecito mudslide in January. So it turned out this forecast led to the evacuation of 30,000 people to avoid the risk of that same sort of mudslide thing happening. And here's what actually happened in the middle panel. is the maximum precip was located in Big Sur. They still got some decent precip in Santa Barbara, but it wasn't nearly what hit up in Big Sur and was much less than predicted. This next diagram on the right shows the difference between the predicted and observed, and you see that dipole of purple and yellow, which shows essentially about a 200-kilometer error in the landfall position forecast of the AR, just a day or two or a day ahead. The color field here is the integrated vapor transport observed, and you can see the red dot is where it hit the core, and it just sort of skirted by Santa Barbara area. And here we see, for example, at 3 days lead time, about 400 kilometers or 300 or 400 kilometers uncertainty is normal. So this isn't unusual to have had that error. Now we're looking at the time integrated IVT because an instantaneous view doesn't tell the whole story. And here we see the time integrated shows the max value, once again hitting up north of Point Conception between there and Monterey. And here on the right is the difference between the predicted, which is the color filled, versus the observed, which is the dashed line. And what you can really see is the AR was originally predicted to hit more of the LA basin and then eventually came in farther north. And we have some physics I won't go into here that we think is responsible for that. But to explore improving that, the aircraft flying out to the southwest of California ideally could have helped with this. So we're looking for cases like this for us to explore with our AR recon studies. Let me turn to that for a moment and show you more what that looks like. These are the two aircraft we're using. We used last winter. One is the C-130. There's two of them we had use of, and then the G4 from NOAA. On the bottom here, we see an image from one of the storms we sampled where we had one aircraft up out of California. This is a C-130. The red line is the track. The image, of course, is a visible satellite image. And then the dots on there are the dropsons that we released. And let me show you what that looks like. Here's an image of a dropson. It's about the size of two Coke cans stacked on top of each other. It's very light, measures pressure, temperature, wind, and moisture as it descends. It takes about 20 minutes with that little parachute to do so from the aircraft at 30 or 40,000 feet. And it radios back to the aircraft, and then the aircraft telemeters that back to the ground, and that data is incorporated into the global weather prediction models. And that diagram on the right shows the integrated vapor transport in color. You can see the west coast of the continent there on the right. The black lines are the tracks and the black dots are the dropsons. We released about 80 dropsons into this storm, and those all got into the global weather prediction models. We're now in the process of trying to look back and rerun those models without the dropsons and explore the difference. It's actually a very complex thing to do, very tough for the centers to do that, but we've got a team now working on it. We have some funding for it, and I'm optimistic over the course of the next couple of years we will have a chance to prove this out. It takes a lot of work to pull this off, and on the left I've got the list of participants in the project this last winter with my co-PI, Vijay Talapragada, who's at the National Centers for Environmental Prediction. He's the leader of the GFS model, which is the nation's leading global model for the National Weather Service, and a number of other colleagues you can see involved there from many different organizations. So we're going to try to do this again this coming winter, and we bring in not only the C-130s, which in this schematic shows the teardrop of that AR, the black lines crossing it. We're sampling it out of Hawaii and out of California, but then you see another black line out of Seattle. That's the NOAA G4 sampling this feature up in the Gulf of Alaska, basically a patch of cold air and instability. And our belief is that the details of that are important, the details of the AR are important, and the details of how they might interact or might not really determine whether we have what we call a forecast bust. So this is our general approach, and we're hoping to do, we did 3 of these last winter. We're hoping to be able to do 6 or 9 more this winter, and then go on to the following year. This now is the 6 cases from last winter. You can see some have 3 tracks, some have 2, a couple have just 1. This happened to occur. Our plans were right when the government shut down twice. Very disruptive, very big waste of money, and we only managed to get 1 aircraft in 2 of those storms because of that. But largely it was a success. The agency folks really worked hard at it. We're based at the university. We kept working either way. and anyhow, we pulled off this in spite of that difficulty. All right, my last slide, I think it is here, is I want to introduce this scale for ARs. I want to highlight that it's been developed, myself in the lead, with National Weather Service participants John Rutz and Chris Smallcombe, Jay Cordera from Plymouth State University, Mike Dettinger from USGS, Mike Anderson from California DWR, Dave Reynolds from Ceres, which is in Colorado, and he used to be a weather forecaster with the National Weather Service for a long time, and Larry Schick, who was Army Corps of Engineers until he retired recently. This paper is now actually officially accepted in final form. So from a science standpoint, this has passed all the muster and it's ready to roll. So what is this categorization scheme? You can see on the left here the color scale and all that, and with the AR Cat 1 being primarily beneficial, AR Cat 3 a balance of benefits and hazards, but you get up to Cat 4 and Cat 5, we're talking about some pretty serious hazards here, potentially like that event with Oroville. Here I define an event by the conditions at a point, a location in space, in other words, a geographic location. How do we determine an event's categorization? Step one is we pick a location. You see the little map down there with the circle on it?
No, we lost it again. Marty, I'm sorry, we lost the visual again.
I'm going to bring it, do this reboot again here. I'm pretty sure this is my last slide. Share program.
For those that don't know, Marty is kind enough, he's a very, very busy person. He was kind enough to agree to do this, but he is on the East Coast at the moment in his hotel room. So we appreciate your patience, and we appreciate Marty.
Thank you, David. I'm really very happy to be doing this. I am motivated as a scientist in meteorology to try to help provide and develop knowledge and tools that are useful. So I really appreciate the chance to share this. So let me see. Can you see anything yet?
It's coming. There you go.
Okay. Were you able to see this before?
We saw this part, and then I think some of the animations dropped out.
Okay. Here we go. Now I see. You see a map at the bottom?
Yes, sir.
Okay. So the first step in determining a storm's AR category is you pick a location, and then you look at the time series of predicted IVT, the integrated vapor transport. The little schematic down there shows the 250 unit threshold. So when the AR crosses that, as it arrives, and then when it ends is when it decreases below 250. That gives us, the evidence there's an AR, and then the max value there, in this case, the maximum value, that becomes our intensity. And that's the red little dot there, gives us the max intensity in terms of IVT. And here on the left, we see how do we determine the final AR Cat value. It depends on that intensity and also on the duration. So in that little schematic of the time series, you see that the AR started at a certain time and ended at a certain time. If the AR is 24 to 48 hours in duration at that location, then the AR category is set entirely by the maximum IVT during its stay at that spot. And in the left diagram, you see that middle column is that situation where the AR duration on the horizontal axis is 24 to 48 hours, and the maximum intensity scales with the IVT. But because the duration of an AR we've proven is very important to its impacts, if it's short-lived but strong, we demote it by one category. So in other words, if the AR conditions only last less than 24 hours, we demote it by one category. However, if an AR stalls and lasts a long time, the hazard really ramps up, so we promote it by a category. Hence the sort of diagonal nature of that diagram on the left. Now one could ask the question, what about, and by the way, one can use this not only looking ahead in forecast, but looking back at what's happened historically. And we did this as an analysis in this paper that the reviewers asked for that event that hit Oroville. And let me show you now what the forecast, or what the observed AR conditions were in terms of categories for that. And I just advanced it. There should be a diagram come up on the right-hand side. And now the color fill here is that sort of blue, green, yellow, orange, red. And the red was an observed AR Cat 5 that hit Northern California and Southern Oregon at the coast. and it reached that little gray star, which is a little hard to see. I should make that white. That's Oroville, and you can see it experienced AR Cat 4, that orange. And you can see the green even went pretty far inland, up into northern Utah and western Wyoming and all that. And the dots on here are interesting. They represent the difference between the predicted AR category and the observed. The large dots are 2 categories in error. The small dots are 1 category in error. And the black ones, the filled ones, are under-predicted, and the white ones, or the empty ones, are over-predicted. So, for example, down on the bottom left, you see Hawaii was over-predicted by 2 AR categories in terms of this storm, whereas Oroville and Northern California and inland a bit were over-forecast by up to 2 categories. So we're hoping to, we're planning to use this winter at our website for CW3E. And we'll be, conveying some information on Twitter. One thing we do is we take National Weather Service information. We'll include it, like their precipitation forecasts. We'll look at the models. We'll look at our own model, and we will put a summary out that explains the AR attributes of the upcoming storm and shares that with people for, as an experimental thing that people can use or ignore as they please. And National Weather Service offices get the information as well. Once again, they can use it or not as they please. But we have this information out there now, and then after the storm, we do a post-AR event summary, and we post these for people to take a look at online, and we're very welcoming of feedback and suggestions for improvement and all that. So finally, I just want to add that we can also have fun with ARs. In Lake Tahoe, they invented a AR drink. It's a very sweet drink. I don't actually like it, but it's sort of playful that someone decided to do that. And then finally, I'll close with this slide, which highlights some of the website for our center, and you can find information on this, and my email address is here as well. So I'll close with that. Thank you very much.